Hello everyone, my name is Joe Lee and I'm your ELSOC Workshop Executive for 2024. Today I've run a Verilog Workshop and planning to edit a recording. Unfortunately, the recording is really not good and unfortunate because the audio is not being recorded and we basically don't get any audio for it. So I'm gonna re-record it. So hopefully you will find the session useful. Anyways, so before I start, I'm gonna tell you where you can access your document, the workshop document. I just made an ELSOC public drive, which is new because I don't know if ELSOC has something like this. But you can go into Verilog Workshop and then find Verilog Workshop PDF, which is something I wrote yesterday. Yes. And you can also find the reference code here, which contains all the code. But of course, I would encourage you to type it out yourself. Right, to access this public drive, which I just made, I have made a QR code, which is this one. Feel free to scan this and access the public drive. Anyways, or fortunately, I'm not sure how organized ELSOC is with the public information, but if you search my name on Google, you find me and go to this, go to 2141. This is the link for the Microsoft Teams today. I will delete that soon because it's ugly. You can click on Verilog Workshop and it will download your PDF file for you. So that's another way you can access your workshop document really quickly. Yeah. So without further ado, let's get started with our actual workshop. Alright, now we're in the virtual machine. So to get started, we of course open our project navigator. Wait, can't really press anything. Whoa, that's not really expected. But sure. Something's I'm holding my G button. Is it pressing? Yeah, my G button's really like to be pressed. Anyways, I think it's done it. Doesn't matter now. Okay. So we gotta start by making a counter. As you see, I've already done this before because I'm a good workshop exec and I prepare for every workshop I do. So don't worry, I will bring you through everything I've done. Let's go ahead and create a new project and name it counter. So top level HDL because we're writing Verilog code. Next, leave these as default, probably should work. Unless you got something that doesn't match this, which you can surely check. And project design summary, it tells you everything, but we're not really interested. We just want to get our stuff working. So when you open a new file, there should be nothing in here. That is okay, because of course we're gonna make something. Let's make a new source. What are we making? We are making a Verilog module. And here's the plan. Okay, I'm going to quickly talk about my plan and we'll get started writing code. Alright, we are currently in OneNote and I'm going to discuss about my plans for the counter, which I will write here. Let's hopefully get our toolbar out. We'll write counter. Ooh. Fortunately, we do have a counter. We can write our counter here. Okay, so what we're going to do, our plan, what we want to do and what we want to observe is essentially a 7-segment display. We have 4 of them. Let's kind of draw 4 really quickly. On the FPGA, we have 4 7-segment display. FPGA development board. And we have 1 digit that we want to actually use. So the digit starts from 0. And what we want to do, we want to do something when we do something. We want it to display something when we do something, and that something we do is to press a button. So we have a switch button here, switch here, and we press it once, it's gonna increment it one time. That's essentially what a counter does. So it's gonna become 1, and then when we press this again, this is gonna be 2. Actually, that one, I think that one is here. 3, and then dot 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 4, 5, 6, 7, 8, 9 goes all the way to 9. We want to keep going, okay? We want to keep going to like 10. 10 in hexadecimal is A, and then B, and then all the way to F. Make sense? Okay. So we want to press this, and it cycles through 0 to F, and then goes back to 0. It goes back to 0. So what are we doing? This is a counter, of course. Yes, we know this is a counter. So we have a 4-bit state machine. So one very important concept I want everyone to know about is what is a register. Let me just write this state machine. Let's go and talk about what is registers. Registers. Okay, very easy and basic understanding of register is what is the cash register. Like, this is a more daily example of a register. Cash register holds your money, right? It holds your money, like it holds up money. It holds money. So register essentially is a device that holds a value. Okay, just like cash registers. I can't pronounce things properly. So this holds a value like 9 or 10 or like whatever you want, depending on how big the register is. Okay, so anything that holds a value in Verilog should be a register. For our context, yes. Okay, so a register needs to have an input, because you need to tell the register what number you want to give it. So this input can either go in like parallel, every bit loads at once, and once you every time you clock it, everything goes in at once. That's how you load a register. A parallel load. A register, you can also input it by shifting 1 bit at a time into the register. Every time you clock, you serially transmit the data into the register. Anyway, but that's not important. Important part is register holds a value. That's the most important thing I want you to know in this workshop. So let me just draw it here just to not keep this too empty. Think of it as a multiple bit flip-flop. Okay, a D flip-flop is essentially a 1-bit register. Let's just say 8, 9, I'm not sure. Clock, and maybe a register. Register always has an output, right? Not too fussed about this. I'm not too sure. Okay, so now let's go back to our plan. Our plan is to have a state. That state is essentially our 4-bit number. 4-bit number. This is our state as well. The state directly goes to the output, okay? Which I'm gonna draw 1 wire just to make it look pretty. 1 big arrow. It's not a wire, it's an arrow, okay? Sorry. This is our state, okay? So let's say our state is 0, 0, 0, 0. And every state machine should have a next state logic in the concept of 2 and 4. I don't want to speak too soon in case I get anything wrong. Okay, now what do we want? So let's say our clock is our push button. Our clock is the push button, okay? Every time we clock, every time we clock, how do I draw this? Pull down resistor always, and VCC. How does this work? Okay. Okay, so every time we clock, we want this state to change by 1 bit. So the next state would be 0001. Now this next state, so every time we clock, our next state goes in, our state becomes next state. So every time I press this switch down, I like to use some different colors. Excuse me. Every time we press this button, this clocks, and the state becomes next state. Okay? But the next state is always going to be state plus 1. Okay, that's our plan. And we have a 4-bit state that counts up. Next state is going to be state plus 1. This is and then we also need an output. The output, we essentially want to feed in a 4-bit value into a 7-segment display value. So segment display, which goes to here. And we also have 4 analog pin, which goes to the corresponding digits. These 7 bits goes to these, like corresponding 7-segment display, like 1, 2, 3, 4. Sorry, A, B, C, D, E, F, G, 7, including this 8 bits. Okay, but here's what we, 8 bits, and these one corresponds to 1, 2, 3, 4. Okay, so we want to turn this 4-bit value. Actually, don't worry about it. We want to turn this 4-bit value, into an 8-bit value or 12-bit value if you like. Okay, that's essentially our plan. So this is to draw a better diagram. This is essentially a binary to hex decoder. Okay, and this is our output. Okay, this is our plan. Okay, so let's get rid of this because it's not important. It is important, but it doesn't reflect the diagram really well. Okay, sorry, that was someone texting me. Okay, cool. So we have a state. The next state is always gonna be this current state plus 1. Depending on what state you have in your exam, this state could be different. But right now, for a purpose of a counter, the next state is always current state plus 1. And then we send the state to the output, which is the binary to hex, and it displays. This is essentially how our clock works. Okay, so let's get back to our code. Alright everyone, we are back in our virtual machine, and it really likes the letter G, so let's tell it to silence itself. Okay, so back to our design. Our Verilog new source wizard. I'm just reading what I see. Anyways, so the first thing we want to make is a module within the code. Module that we will use, and that is the binary to hex. So let's make a binary to hex. Let's call it binary to hex because that's a very original name, designed by myself, which is not really, but sure. Module name binary to hex. That's a really good name, right? Or you can call it decoder if you want to. And just finish, and you get an empty module. First thing you want to do is to this is not a part of the workshop, so whoa, I did not meant to do this. I really like the letter G. Anyways, you can just go ahead and copy and paste all of this code because this is not meant to be a part of the workshop. You can go ahead and copy and paste this code and put it here. I can still explain it a little bit. So what is happening here? So 7-segment display, this is SEG. We have a 3-bit input. Actually, no, 4-bit input, I'm sorry. 4-bit input bus. This is how to declare a bus. Okay, I'm going to type it out just so you can remember it better. Input 3 to 0. What did I call it? I forgot. B. B. You can call it anything you like. You can call it Joe, you can call it Henry, Tom, whatever. Okay, but best style is to call it something you would know what it is. In this case, B is a pretty good name for B. Now, register. Why did I use register here? Because, as I said earlier, register is something that stores values. Anything that stores a value is a register. And essentially, when you use something like always at, everything inside that you assign to has to be a register because you're essentially assigning stuff to segment, and segment needs to hold it, right? I know this is a combinational circuit, but we are using sequential circuit method to make this combinational circuit, which is the reason why we do this. So we have always at B begin. Basically, always at B means whenever B changes, we do this. So whenever B changes, or let's say B changes from 0 to 1 or 1 to 0, we do this. So let's see what B is. It says, oh, when case B, when B is 0, 0, 0, 0, segment becomes this. When B is 0, 0, 0, 1, segment becomes this, and so on. Okay, so basically all of these are pre-written on the document, saying these are the 7 segment values. This is a 7 display for 0. This is a 7 segment display for 1. This is 2, 3, 4, so on. So you don't have to spend your life writing this. Okay, cool. So that's basically it. The decoder itself isn't too scary. Now let's go ahead and make a new source. Go Verilog module, and what do we call it? This is our main sequential circuit, right? So let's call it counter. Right, counter is cool name, very original. Now press next, and press next again, and finish. So we get an empty module. This time it is actually empty. Okay, here's the main part we want to focus on this workshop. Now, input, we have an input. Every time you start making a module, you want to declare all the input and output. So what input do we have? We have our clock, which is essentially our push button. Okay, basically our push button. You can call it push button if you want to, but I'm just gonna call it clock because yes. Every state machine, you want to have a reset button. That's just good practice. If your state machine gets stuck at some place and you can't make it go back to 0, you're gonna have a miserable life when it doesn't work. So let's be a good engineer. It's not the words to say it. My brother taught me to say it. Reset. Let's have a reset. Good 2141 student. Okay, we're gonna be a good 2141 student. Have a reset here. Now, output. What output do we have? We have our 7 segment display. We have 7 segments with the .8 outputs. So let's do 7, 0, C. These are each segments of a display. Let me just Google while I have the chance. 7 segment display. 4-digit image. You can see we have usually a 7 segment display has my connection is not secure. Usually you have 1, 2, 3, 4, 5, 6, 7, 8 pins and 4-digit pins, which is what's on our FPGA manual. It's okay that this is the 8 pins comes from C, and the other output we call it the anode, which selects the digit. Okay, very cool, right? Almost as cool as me. Now, a very good practice, if you read this manual, is basically, did I do this? Oh yeah, this is the image, don't worry. We put in the input, and the very good practice is what our previous lab demo has taught me, is to follow a certain structure every time you do a state machine. So we have signal declaration, which is register. So let's put in signal declaration. Let's try to put in some padding to make my style better. So we always want a current state and next state. Am I correct? Of course, I'm always correct. Not really, but this time we want it to be 4-bit, right? A 4-bit register, 4-bit because we are counting in 4 bits. State, next state. So we're declaring two state like register. We're declaring two registers. Remember, everything that stores value is a register, including our state and next state. Our state stores a value, so we having register, right? If you don't use REG, it won't work, and it will be really sad and pop out some errors for you to take care of. Now the next thing you want to add is state register, which I've probably written in the manual. Not manual, the document. Yes. And we put in always at pause edge clock, comma, pause edge reset. So something happens every time this happens, okay? And every time you want to begin, you type begin. This is not C programming. You don't get to bracket your stuff, which is a little bit sad, but we are not the one writing Verilog. We're not the Verilog designers. We ask them what's going on. Anyways, next thing we're going to put down is next state, which next state logic, which essentially means, oh, next state is going to be like this. So always at star, always at star. One moment, I can't find my keyboard words. Begin and this, everything, the next state logic happens in here. So yes. So I should have a diagram in here. Hopefully it loads. Yeah, there we go. Cool. See if I can close. Oh, it really doesn't like it. Okay, well, I'll just present it here. And finally, we have our output. Okay. Normally, you want to put your output inside always at some sort of always at, but I'm just gonna leave it outside because we are going to use our module. Okay, can I quickly at this point interrupt a little bit and just talk about this? Our counter is our main module, so we need to set as top module because we are going to be using binary to hex inside counter. Okay, cool. So this is the diagram that I drew earlier. So we have our clock, which is our button, current state, which is our counting number, and the decoder and the next state. Okay, cool. This is our diagram. So signal declaration, this is needed because we need to have some register that holds our state and next state. Okay. Yes, we need registers to hold state and next state, and they're both 4 bits. That's why I have this line. State register. Okay, the fun begins. Now, state register. Where is the state register in this diagram? Right here. This is the state register. So all the magic happens here. So basically what this says is every time you reach a positive edge, pause edge, the clock reaches the positive edge, something happens. Let's ignore this for the moment. I'll add it later. don't worry. Let's ignore this for the moment. Okay, state becomes next state. So basically, as I drew before on OneNote, every time we clock, state becomes next state. Okay, so every time we clock, this value becomes this value. Okay, that makes perfect sense, hopefully. And let's leave it like this for the moment. And the next state logic, as I said before, next state logic is always going to be counter plus 1, which is basically state plus 1. So next state equals state plus 1 and semicolon. Okay, why did I use this and this? What is this thing? This is called a non-blocking operator. I'm not sure what it is. Yeah, non-blocking. You just call it non-blocking. So if you write stuff like this, everything is going to happen in parallel. But if you write in this is called blocking. This is going to happen in a sequence. So basically, this is non-blocking is going to happen first, and then this is going to happen. You can still put this in here, but the fellow academic director Jonathan Dang has decided we should use equal sign because we want this to happen after this, which makes sense because you don't want to. If this happens before this, then your next day is gonna kill up. Your next day is gonna be keep going. Okay, like I can give a quick example. Like let's say state is 0, next day is 1. Yes. Next day is 1. Actually, you know what? I think it's okay to put this in here. It should still work because this is essentially a combinational circuit. Okay. So, and I will care about reset later, but now output is going to be a binary to hex, which is we're trying to instantiate. Every time we instantiate something, very important, every time we instantiate something, we call the module name, which is this one. This is our previous module. We call the module name, and then we give it a name. What name do you want to give it? Like Cujo, of course. I just try to make it really figurative, or yes, you can call it decoder, or like some decoder cool. Or like cool decoder, right? Okay, and we add parentheses and input what parentheses. This module has a 4-bit input and a 7-bit output. So our 4-bit inputs is going to be our state, obviously, because if you look at our diagram, the state goes into the decoder. Now the output is going to be C. Right, so output is going to be C. So we can just type C in here and semicolon this. Very cool. Now we're also going to assign. A equals 4B1110. And then we will have, why do I do this? Exactly, why do I do this? So if you look at 7-segment display, you have 4 digits, right? 1, 2, 3, 4. So you want to keep these things low, and you want to keep these 3 digits off. So that's why they're 1. If you look at the reference manual, this is a common anode. Common anode, yeah. I think it's a common anode. I might be wrong. Ooh, not interested. Don't worry. Yes, common anode. Anyways, the idea is we want to let only one LED turns on, which is the last bit. Okay. Now, very quickly, I want to talk about this the reset thing. So when we press the reset button, we want everything to turn to 0, right? So we can essentially have another pulse edge reset. Wow, now we want this to only happen at clock. So to your surprise, you can actually write if statements in an always at block. So if reset equals 1, begin state, what do you want state to be? Equals 4-bit 0000, else begin, sorry, and else begin. You see, Verilog really loves English letters, so we have to roll with it. And, okay, cool. So what it means, if positive edge of reset is reached, if reset becomes positive edge, it means you press the reset button. State becomes 0. So state becomes 0 like this. This doesn't run because your positive edge, the reset, it's not else, it is this one. Now, if you press the clock signal, clock is gonna reach a positive edge, and state is gonna become next state. Cool, that's what we want. And also, let's kind of let's put next state as 0. I don't think we need it, but why not? Again, we planned it together, and Jonathan thinks we should have it. So, if reset equals 1, essentially we want to have everything to become 0. Begin, end, else, begin, end. So when reset is 1, at any clock, next state becomes 4-bit. So basically we turn everything into 0, which makes sense, right? That makes sense. Cool. Now we're essentially done with this. We are done with this, so we need to make a UCF file. So I'm gonna add a new source. Sorry, my bad. New source and implementation constraint file. I'm gonna quickly write the file name. What do you want to call it? I want a really original name. Okay, let's not waste too much time on this. Just call it counter mapping. I'm not really good at giving names, but I'm really good at naming children's. Okay. So, as you can see, we have prepared you really cool stuff. Here, I've left everything else blank. You can just copy and paste and put it here. Unfortunately, these are left question mark because I like to make your life sad. Not really, but it's a good way to learn. Okay, I'm going to quickly talk about what we put in these question marks by looking at the reference manual of this FPGA development board. Okay. Okay, now we're in the Diligent Nexus free board reference manual, and I'm recording this afterwards because my audio was broken. So as you can see, we're scrolling down to this section where there is a bunch of pins labeled with these pinouts like T17, T18, U17 on this thing. So this is what we want to put in the UCF file. So that replaces the question mark that I kind of used to troll you guys. So replace all the question mark with all the corresponding pins on this diagram. I'm back, and I figured out why I really lost my G button. Because when I press Windows G to record the screen, it starts spamming G. Okay, so now let's go back here and referring to the, according to our lab, what's it called? The reference manual. And let me just quickly pull out the reference sheet. Next sees free FPGA board reference manual. According to that, we want to put C0 to N13. Oh, it doesn't really work, does it? 1 second. Yes, N13, L14, N14. I love my life. M14, U14, U18, sorry, U17, T18 and T17. Okay. Now, as I said, we want to assign a switch to A8. And we want to assign reset to C4. And again, we want to assign all of these to 17, P18, N15, N16. Cool. Everyone happy with that? Hopefully. Now this should work. So we just need to try really hard to actually, wait, how do I do this? I kind of forgot. Sorry about this. That's really strange. Okay, I'll get back to you. Yeah, that's really strange. I don't see why this is happening. Is it in here? Okay. Ah, there you go. Could it be this? Maybe it's this. Whoa, 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 whoa. Where's that tab? Okay, look at this. I found it. You basically want to drag this out. Use utilities. Look at the counter. Let's just press generate programming file. Hopefully magic happens. Apparently we have an error. But the error is okay because we can always debug it by reading the error message. Mix of blocking and non-blocking in next state. Oh, that's why Jonathan wants to. Okay. We want to use this. Arrow equals, okay? So I was right. Because I'm cool. Let's try again. Reading always helps you. If you don't know stuff, please read it. Error sometimes synthesizes. Ooh, something's wrong with map. Let's look at what's happening. If you see an error, don't get stressed. You can always time driven by. Okay, so here's the one. I want to take this chance to talk about what's important here. When the error is map, when the error is translate, you can always it means the problem comes from transfer transferring your code into FPGA things. When the error is at map, it means your problem is in UCF. So that's a good starting point. Time-driven phase encounter an error. Okay, so I'm looking at what's happening. Okay, so basically, the current problem is it doesn't really like us using A8, so that's okay. If it doesn't want us to use A8, we will not use it. We have to do a bunch of these to suppress this error message. So if we really insist us not to use A8, we can use something else like C9 and hopefully save this. Save all of them. And let's try again. So translate is basically making it into map. Map should hopefully work. Error should be fine. Always errors. And everything seems to be working fine. And generate program file here. So we should have our program file on. Apparently we named this Tuesday works because we've been working on some Tuesdays and it magically worked. Where did I put Tuesday work? Right, share folder. Tuesday work. So you can find the files in here and put it in your FPGA and it will start working. Yes, unfortunately I don't have a video. I have one. But what you will see essentially is basically when you press that button, it doesn't really count properly. Well, okay. It's a little bit sad I can't show you, but it's okay. I have another way of showing you, which is called an XI. So basically, let's go back to the file that I originally have. It's basically the literal exact same thing, so don't worry about it. New counter. Because we've been working in. So these are the exact same thing with a lot more comment because I've been working on Jonathan with this and we try to tell each other useful information. So we made a simulation. You can copy these code if you want to. These code. So we can have a look at what's happening here. Right, okay. It's a little bit fiddly. iSim. Like, I don't really have an FPGA in front of me, but I can always show you the simulation. So as you can see, every time you clock, this changes, right? So this is 0, this is 1, this is 2, this is 3, and A becomes 110. Right, okay. So that is essentially what we have done in the workshop. So unfortunately, if you look more into the workshop, we have another section. Me and Jonathan tried really hard to make this happen, but we didn't get to there unfortunately. So I can quickly talk about it if you're interested. You can always try this by yourself. Right, okay. Let me go to OneNote and kind of share what's happening here, okay? In the workshop today, some people managed to actually get it working, which is very exciting. But what happens is, basically when you press the button in the FPGA, or when you toggle a switch, the number doesn't always go from 0 to 1, 1 to 2, 1 to 3, 2 to 3. It always tends to, let me just pick a cool color. it always, when you press a button down, it always tends to like jump over a few numbers. And when you release the switch, you don't expect anything to happen, but it happens to like go a little bit more. So what's going on? Basically, what actually is happening is called noise, and it's basically it's called bouncing, if that's a word for it. So basically, when you press a switch, this is your finger. I'm very good at drawing. Let's try again. When you press a switch, your expected signal is gonna be like this. So it'll look like this, and when you release it, it's gonna look like this, right? Whoa, 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 whoa. This is what you expect, but in reality, this is what happens. Very sad spikes. That's causing all the life problems to arise. Which is why, when you press a button, this skips a little bit here, you skip a little bit when you release the button, because there's a little bit clock here, right? It releases the button, and that's not what we want. So what we can do is something called debouncing. So here's the plan. So basically, you have your signal like this. This is your signal. So what your debouncing circuit should look like this. Okay, you can program this in FPGA or Verilog. There's like a number of ways to do it, but this is the classic way. I'm gonna keep it simple and make it like 3 blocks. But the more blocks, the merrier. Okay. D and Q. You have 3 D flip-flops. Essentially, you can have much as you want. You can cascade more, but I'm gonna stop here because we don't want to keep everyone sad here by watching me drawing flip-flops all day. Okay. Now let's do 3. We can also put this in. Okay, so your noise, let's use another color. I'll have 3 here. Your noise is going to look like this, right? So what is it really? It is, let's look it from this side. The signal that's going in is 1 0 1 0 1 0 1, and it stays 1 forever until you release the button. When you press 1, when this clock, okay, there's one thing I didn't say is there's a constantly running clock that is connected to all the clocks. This is constantly running, constant clock running, and you can always find a clock signal in the FPGA. So when you clock it, the first signal comes on, and this output pin will turn on, right? Now when you clock it again, these values are going to shift, and hopefully this value will go in 0 1. And because even though this is 0, it's okay because this is 1, this will stay on, right? Now if you clock again, you have 1 0 1 1, and then this is gonna stay on because this is 1 and this is 1, right? So even though there's like noise in here, you can clearly see like zeros in here, but because of this flip-flop configuration, this is gonna turn on. The way to improve sometimes it is very difficult to capture. Sometimes you fail to capture the 0 in the correct spot. The way to increase the likelihood, like make it less more likely to debounce, is to increase this frequency. That way you push in less data, which is more likely to skip through all of this crap. Now your output signal, in this case, in a perfect synchronization manner, your output is going to look like this. Oops, sorry. Your output is going to look like this, which is perfectly debounced. Now, you can try the case for the negative edge, which should be the same, except everything turns to 0 after everything is off. Okay? Well, that's it for the workshop. Oh yes, that's not it for the workshop, because we are going to discuss what happens in the tone generator really quickly, and I'll leave you to do it. Alright, let's quickly talk about the musical tone generator, which we haven't done in the workshop because we ran out of time. Unfortunately, our time in the lab is actually limited, so this is very unfortunate. So, in the musical tone, me and Jonathan decided to call it musical tone. What we want is we have 8 switches. These are switches, okay? On the FPGA, they are switches. So when we toggle this switch, the buzzer plays a note. When we toggle this switch, the buzzer plays another note. So you can basically see when you press different buttons, it's gonna put some different notes on the buzzer. Let me just draw this buzzer a little bit more nicely. Speaker. This is actually a speaker. Now, the way we do it is first we need a timer. So the FPGA should have a constantly running clock, which is located, if we read the manual, let me just go to the manual really quick. Right, as you can see, we go back to our reference manual and try really hard to scroll to this point where it's the oscillator. So the oscillator oscillates at 100 megahertz, mentioned in here, and it's located at V10. So the V10 is essentially a clock oscillating at 100 megahertz, and that's what we want to put in our clock because we don't want to be oscillating it by ourselves. So yes. Okay, so let me just, actually I can't stand this being too thick. Okay, so you have a constantly running clock, which is going to V10. V10. So this is oscillating at a frequency that we can't hear. We need to lower the frequency to something that is actually audible, like 200 hertz or like 1000 hertz. That is actually what we can hear, whereas this is like 100 megahertz, and we can't hear it. We can't hear this noise because it's out of the audible range. So what we want to do is we want to have a counter somewhere, a counter again. So basically this thing resets after you count to a certain number. So you have your timer. Again, this is a state machine, okay? This time you have a clock and your state which is the counter again. This time you have 32 bits because that's actually we actually need a big counter to make something audible. Again, what happens in the counter? What is next state? Next state is state +1, of course. Right. And next state also has a condition, which is, let me just erase this. We have an input, which is also 32 bits. And I'm gonna put it here. and if state is equals to input, state goes to 0. Actually, let me just. This is what we want to do, okay? And it's perfectly implementable in logic. And what we want to do here is to we want to flip the output. Okay. Every time this happens, we flip the output. Feel free to look at our code and have a look at what's actually happening in detail. But generally speaking, this is what's happening. So now you have a timer that whenever this counts to some certain number, it resets. So we can create any frequency we want. So whenever we press a switch, the switch goes to an encoder. Which goes to a 32-bit value. Yeah, 32 bits. Which this 32 bits goes directly into the input. Goes to the input and it goes to whatever this is, and there's an output here. We don't actually, this is no arrow here. The output is here for some reason. So this oscillates at whatever frequency we decide to. Okay, that's basically how the tone generator works, and I'm going to attach a video here of it working, just to be a little bit funny. And that's it for the workshop. Thanks for watching. See you next time.
Do you want me to hold film for you?
It's okay. So low volume. Let's put here. Okay, that's enough.